Well, hello, how you doing? We're supposed to start our seminar very, very shortly, but before we do, I'd like to have folks be aware of the exit signs in case we need to leave the room for whatever emergency may be necessary. Um, for those that are on the internet, we strongly encourage you for the Q&A to send your emails to sierra.rm@calepa.ca.gov. This way we'll have a chance to take them in enough time before we end the seminar. Otherwise, we may be in danger of not taking your questions. So with that, Ash?
Good afternoon. The Center for Built Environment is one of the unique assets and resources available to California's energy savings as well as air quality improvement policy decision makers. And it has been around for several decades, and it enjoys not only Professor Ahrens as well as Dr. Wei Zhang as very major contributors to developing state-of-the-art approaches to thermal management, energy reduction, and development of net zero buildings and topics of that nature. I could say more, but I'd like to conserve time for the presentation, which should be fairly interesting and should also communicate a great deal of perhaps new ideas that could percolate and become standard operating procedure in California buildings. Without further ado, Professor Ahrens.
Thank you, Ash. Good day. My colleague and I are going to present the projects that we did for CARB, but also frame it in a larger context, which is the whole issue of air movement as a way of conserving energy in the conditioning of buildings. And my colleague is Dr. Hui Chang here, who will talk in the middle of this presentation. She will give some of it. So the energy saving, the role of air movement in buildings is it has immense energy savings potential, but it also has large potential for increasing comfort of the occupants, or at least keeping it the same as it is in a neutral environment. And it has some air quality effects too, because I know that traditionally CARB is interested in indoor air quality. We have a kind of a type of air quality that's called perceived air quality, is how people perceive their environment, and then there's the actual air quality. And air movement has a role in all of these things. So we're going to divide the talk into a discussion of the general comfort issue first, and then there'll be something on the role, the projects that we did for CARB in the second category, and in the third category on perceived air quality. And then we'll talk about barriers for the use of fans in practice and future opportunities that we see. So there are 4 factors that affect thermal comfort, and these are all embodied in the heat balance equations that are used for determining if you're comfortable or not. They are ways of dissipating the heat that's generated internally in your metabolic system. It has to go out at the same rate as it comes in over time. And so air temperature is one of them. Your skin temperature's got to be higher than the air temperature over time. So is the surrounding temperatures. So the effect of the surroundings exchanging energy with your body surfaces by radiation. It's kind of averaged together in something called the mean radiant temperature, and the mean radiant temperature and the air temperature roughly have the same effect on your comfort. You could add the two together and divide by 2, and you've got a pretty good estimate. in most situations indoors. Humidity also affects your comfort in that it affects your ability to dissipate evaporative energy from your skin. And the hotter it gets, or the more exercise you're undertaking, the more likelihood you're going to sweat, and the efficiency of the evaporation is a big heat removal opportunity for you. And so the humidity of the air either impedes that or increases it. It's not a super powerful effect, in spite of what you might think. The air temperature has a larger effect, as we'll see in a moment. And then there's airspeed. So airspeed also increases the heat dissipation from your body, both by removing sensible heat, by basically increasing the heat transfer coefficient from your skin and from your clothing surfaces, but it also increases the evaporation rate of the sweat or even just the moisture that's inherently in your skin that you don't even feel. All that is increased by airspeed. So since the 50s, since air conditioning became used kind of universally in commercial buildings and began to also be used in houses, we've always focused on the first three of these things. Carrier's air conditioner was a thing that was designed to remove humidity, in a paper printing plant. And he had to know the air temperature, the MRT maybe as well, and certainly the humidity. And so those things are all taken into account in the way the comfort standards are shown on the psychrometric chart that I'll show you shortly. Airspeed has not been part of that, the comfort zone, and it's really been considered for various historical reasons as only something that's negative. It's going to cause you drafts. You got to avoid it. You got to go to great effort to make sure all these diffusers in your space don't produce a perceptible air motion, because it'll be bad. So here's the standard for comfort. The comfort zones is a red and a blue one, and that's the summer and winter, but they refer to different clothings that people have at those times of year. Here's the summer and winter. The actual set points, and these zones are supposed to satisfy 80% of the occupants. Occupants have different thermal requirements. They have different clothing, different metabolic rates, and especially they have different internal physiology. And so there's a difference in the population. These zones are supposed to satisfy 80% of the population. The radiant temperature is taken into account on this by the use of something called the operative temperature. That's on the x-axis here, which is basically the dry bulb temperature and the radiant temperature, the mean radiant temperature averaged, as I mentioned before. The actual set points in buildings are actually kept at in a lower zone than what is shown on the chart. Building engineers, for a variety of reasons, are very conservative, or maybe they want to show that they can do cooling, and for this and other reasons, the set points tend to be in a narrow range, much narrower than the comfort zones, and they tend to be in the winter zone year-round. Those are the set points. The actual temperatures are even colder than the set points. So here you see the comfort zones again. This time the vertical axis is relative humidity, but otherwise those zones are identical. And you can see that set point range again on the red lines, but on the little dots there represent each one a building. 95 office buildings that were studied in a large study of office buildings, and the actual temperatures measured are in the winter comfort zone only, and they're on the cold side of it. In fact, they're often uncomfortably cold, and that's what they observed when they surveyed the occupants as well. There's a variety of reasons why we're overcooling buildings in the summer. It's a known fact, and this study is one of the first to have shown that. And a lot of it has to do with set points for ventilation air, minimum rates of flow that are passing through the terminals in your room. But that's a different topic that we have to talk about at some other time. This is the underpinning of this talk. It's if you can widen that range that you saw on the psychrometric chart, or the one on the last graph. These are the temperature set points on the x-axis. if you could widen the range 1 degree, let's say, 1 degree Fahrenheit, you will, on average, in all these different climate zones here that you can see, save on your HVAC energy the following percentage. 1 degree Fahrenheit gives you about 5% savings. And those HVAC savings on the left side are total HVAC, summer and winter. So even if you only save in the summertime, the numbers here apply. So what you can see is that the numbers are very large. Yeah, my cursor is showing up here. Okay, so and especially if you're in a place like San Francisco or Fresno, you'll see that these curves are at the upper part. If you were able to run the temperature up, the summer cooling temperature to 75 instead of 72.5 or whatever the mechanical engineer is using, you will get a 30% savings in total HVAC in your building. And if you could run it up to 80 degrees, you'll get a 55% savings here. That's vast. There's nothing else that can give you that kind of saving. So then you say, well, gee, but who wants to be at 80 degrees? You know, that's not acceptable, isn't it? This has been published. This was actually done with CARB support to put these simulations together. They're very intensely, the simulations were very intensely done. They use the DOE standard buildings. They use a whole variety of assumptions, which are all in the publication, which, and they've been repeated by other software programs and other building models, and they basically come out the same. It's a pretty clear thing that if you are able to play with the interior range of your environment, the temperature part of it, you have the potential to save a great deal of energy. All right, so now let's go back to air movement, because as you know, as you probably guess, air movement's going to play a role in this. And let's find out a little bit about what people think about today's air movement in buildings. These are buildings that were surveyed in the ASHRAE database, right, that, which was probably 100 buildings that where people were surveyed for their sensations and for their air movement preferences, their temperature preferences, all sorts of things. But this is the relevant chart here. Of all the people in that survey who were mildly cool even, all the way down to 0.7 thermal sensation scale, and that's a value that's considered uncomfortably cool by the ASHRAE standard, all the way up to 1.5, which would be slightly above, it would be above the warm sensation. Of the people in this range, which is most of the people in the entire database, 52% want more air motion. And the number that want less air motion is something like 4%. This is a shocking thing, it's given that the standards focus only on limiting the amount of air motion that you can have in a space. And they're trying to keep it at slow value. And also, they also ask if people are satisfied with their environments and is the environment acceptable? And so there is a group of people who find the environment unacceptable. That's the purple pie on the left there. Of those people, what are they complaining about? Are they having too much air motion? Are they uncomfortable for that reason, or are they having too little? Well, you can see that they are uncomfortable because they don't have enough air motion. They're complaining, they're saying in their preference votes, that particular part of the population is calling for more air motion. So, this is something interesting. So let's look at an example just to make this colorful. What's possible if you had more air motion? And here's an example. This is a zero net energy building in Phoenix, Arizona. It's a large construction firm, and this is their headquarters. And this is a building that doesn't turn on the air conditioner, the cooling, until it's 82 Fahrenheit. Right, that's 28 Celsius. And you can look at the building here. You can see that it's got operable windows. You can see the windows in this particular, at this time, are open. But it also has fans, which you don't see very well because the blades are turning. But they're up there, they're above the workstations. And so the question is, how satisfactory is a building where it's kind of a 50s building, right? It has operable windows. It's got some fans. They used to be, ugly kind of Victorian style fans, but but they're turning into space. In this case, they're more modern looking and better looking. What do people feel like in a building that is basically not air conditioned until you're at above 82.5? So in CBE, we survey lots of buildings. We've surveyed, I think, 900 buildings now. At the time this was done, we can compare this building, the so-called DPR building, against about 400 or 300 of our buildings on the database. And so looking at the satisfaction scores that people have for thermal comfort about buildings, on the vertical axis you get the score, which goes from the median, it goes positive and negative. And then you see the percentiles of all the buildings that we've tested. And each building is one of these blue diamonds. So all the buildings, each one of those is the score for that building. And on top of it, you can see some green buildings that have LEED ratings, because they're scattered across the thing. And then you see that the DPR building is actually at the 91st percentile. So this building that doesn't cool till you're at 82.5 is better than most of the buildings in our entire database, which in this case I see is 270 buildings. And there's also spots in there for mixed mode buildings, which this building also is, because the windows open, it air conditions and has central cooling. So now we're going to see, how does the engineering profession deal with the issue of air movement in buildings. And so there's a couple of definitions here. There's you've got windows that open, and these are termed naturally ventilated buildings. And if they're in naturally ventilated mode, they're not running their air conditioner at the same time or heating at the same time. And that's good, and that's kind of the way it's assumed. There are also these ceiling fans, which you see in the right picture. And that building also has operable windows, some of which are open. And so these produce air motion inside too, in a more controlled way than the operable windows. So about before this project began, about 2004, there was a new standard put into the ASHRAE standard for thermal comfort, standard 55, that was called the adaptive model. It's an empirical model that is based on the observation that if the outdoor temperature goes up and down, the indoor temperature can also change proportionally to that. For example, if people wore more clothes in the winter, you'd expect the indoor temperature, the comfortable part, to be at a cooler temperature. So the vertical axis is the indoor temperature, the outdoor is some kind of measure of the outdoor temperature. And the interesting thing about this one, well, first I should say this was adopted in 2004. It's very, very limited. You can only use it on buildings that are naturally ventilated only and are only in naturally ventilated mode. So if you got an air conditioner, you can't use this thing. There's a lot of, this model though, limited though it was, caused a groundswell of interest worldwide. And it's now in standards in Europe and Asia. And it's kind of underlying a lot of attempts to have more natural ventilation in buildings. You should notice, looking vertically, that that's a 13-degree Fahrenheit range in the comfort zone. This is from the 80% acceptable limits are quite far apart. And they don't really know exactly why this is, but there have been studies done, including some by our group, to try to see, is it because of clothing? Is it because of perceived sense of control that people have when they have access to a window? Or could it be the air motion that they have access to? And then on the cold side, maybe something to do with mostly clothing or radiant systems. So it's kind of unknown, but it's in the standard. It's progress. A lot of people are talking about this and worrying about it. But for the big mass of buildings that have air conditioning and cannot be considered naturally ventilated during large parts of the year or any part of the year, there was a need for some kind of additional provision for comfort with air motion. And so this is now a figure in standard 55 as of 2013. And it's been revised in 2014 a bit more. So this is the current version. And it shows at the bottom, under operative temperature there, it shows the 2 comfort zones, the 0.5, the summer one and the winter one, and the temperatures that are down at the bottom of that border represent the comfort zones that you saw on the psychrometric chart at the beginning of the talk. So that's what it is. And as you increase air motion up the vertical axis, the zone shifts to the right because you're getting additional cooling taking place from the air motion that's provided by the vertical axis. And so it shifts over to the right, and you can measure out the amounts there in Fahrenheit if you want it. It's up on the upper axis. One of the interesting things about this representation is that the main contours are all based on something called a standard effective temperature, which is based on a model of human heat transfer and heat thermal regulation. It's well accepted. I think these figures are fine. But within it, you see there's a light gray zone and a dark gray zone. And the light gray zone is air motion when the occupant has no control over whether they have it or not. It's something an architect or engineer could impose on an occupancy. And that would be considered acceptable by ASHRAE. The dark gray zone is you have to have control. The occupants have to have some way of controlling the air motion in that zone. And it's defined as occupants in groups of, I believe, 10 or 8. They have to be, groups have to have access to some kind of control. It's also defined in terms of square footage of floor area that represents local control. So in that zone, you can't go up to those high speeds. You can't impose them on people without giving them some recourse. Now, where does that middle line, that dividing line come from? That's very interesting. That comes from empirical studies, intensive empirical studies, along the lines of the ones that made those pie diagrams of acceptability in buildings. We found that basically if people are even mildly cold, that they want air motion. They want 0.2 meters a second, 39 feet per minute of air motion at temperatures that are actually slightly cooler than neutral. And they don't want to have that considered as draft. They want more air motion. And as you go up, you basically end up following this SET diagram to get the full range. The 0.8 meters a second, or about 130 feet per minute limit there is really not related to thermal comfort at all. It's related to blowing paper. And so that's kind of put in there. It's sitting on top of it. But there's no upper limit to the comfort zone if you have local control. But as you can see, once you're up above 300 feet per minute on a person, the lines are pretty much vertical and they're not cooling you anymore. So there's no point in going above. All right, so that is now in the standard. The old draft risk models are gone, so that we don't have to worry about people, engineers worrying about being sued about having some number that's above some very, very low limit. They can actually now play with air motion as a variable. We consider that a major fundamental contribution, because you basically can't proceed unless you get that stuff corrected. And the correction is based on empirical results from buildings, so we feel confident in them. All right, so now we're going to implement the air motion in the space. How are we going to get this air motion to surround the body? The air motion can actually come from the sides or from below or from above, but the most common one, the ones you see in the pictures, is the easiest access to most occupants is from above. You see more of the ceiling than you do of the floor, and you could be blocked by furniture and things like that when things come from the side. Nonetheless, we're going to talk about all types of air motion later, but starting off, we'll talk about an overhead fan study. Now, for overhead fans, they've been around forever, since electric motors were commercialized. In spite of that fact, there is very little guidance that any architect or engineer can go to find out how to space them to get them to effectively cool an occupancy. Simply absent. Designers, we know designers who've tried very hard to design buildings with them, and they basically had to totally guess what the spacing was. And some of them have missed, and some have been done well. So that's something that needed progress. So the objective of the CARB study was to test a bunch of situations on the list there. We're going to test them at 82.5, which happens to be the same temperature as that Phoenix building. And then we did some additional tests at temperatures above those numbers, and more humid ones too. So in this test, the first one, we arranged a kind of a fan thing where we could have fixed air streams down on people who are working in our environmental chamber there. You see a picture of the environmental chamber. It looks like an office building. It's about almost 300 square feet. It's got windows on two sides. You can set it up to look like a real office, and people do real office work while you do the tests. Overhead, we had this wonderful fan that is a DC fan. I'll be talking about this more. This fan uses 6 watts to blow as much air as most ceiling fans. And we could set it up in 2 different ways. We could have it fixed, blowing down, or we could make it oscillate. We could oscillate through 2 axes. And the ones that we're showing here are as 1 axis. And so we had people sitting side by side, the people on the left, and up above in the diagram you can see that the fan's in the middle, and it's blowing side to side on them. And then we had these people on the right, they're sitting facing each other, and the fan is up above in the middle, and it's oscillating front to back on them. Not to back, just front to front. So this is the test setup, 82 Fahrenheit. People had summer clothing, 0.5 clo, short sleeve shirt. And here is where that point is on the ASHRAE comfort chart, the one that we saw before. This cursor will come up. Here we go. So it's to the right side, the hot side of the still air comfort zone. We're predicting that people are going to need some air motion, at least according to the standard. And there is over here. Sorry, this cursor is very slow. It doesn't appear. Okay, you can see there's a dotted line to the right of the red dot on the 82.5. That dotted line is the extreme cooling that one might expect from air motion in buildings. That dotted line went in the 2013 version of the standard as a function of, as a result of this extended air motion figure that we showed you before. So on the still air comfort zone, it shows how far the comfort zone we feel can go if you have air motion. And you can see that we're well within the boundary there. This is not an extreme test condition. And we'll show you some more extreme ones later. But take a look at what the 82.5 gets you. It gets you 60% savings in the green zone, which is San Francisco. And the lowest possible one is Duluth, where they don't have any cooling. And even there, it's going to be, for an office building, it's going to be like a 30% saving. Different configurations, we do different air speeds, back to front, fixed, and so forth. The results are a little disappointing looking to us in that there's hardly any difference in the results. The left bar is the no fan situation. And we're at 82.5, and basically people are voting that they're comfortable. Just about 25% of the people down at the bottom of the box and whisker plot are down at the just uncomfortable neutral line. But by and large, people were comfortable throughout all these tests. And we were kicking ourselves thinking we should have maybe, raised the temperature a bit. But what we do see from the results is that the oscillating fan is, the fan is better than the neutral case in every situation. And the oscillating fan is less good than the fixed fan, which are the bars over on the right side. And the fixed fans are either coming from the side or from the front. The front seems to be the best, or they're coming straight down, which is the below. All right, And so why did the oscillating fan not work? Because we're kind of hoping we could get a lot of benefit out of these 6 watts. We might be able to sweep it across a whole lot of people and say cool these people in this building for 2 watts per person. And I'll give you a kind of a example. This is the heating, the cooling of a central system of a person it takes you 500 watts. So we've got a couple of orders of magnitude savings here. How much can we get out of it? Well, this was our oscillating condition, which was actually the disappointing part. We had about a 20-second burst when the fan was swinging across your head. 1.1 meter height is head height when you're sitting. And then there was a 16-second kind of hiatus while the fan was over at the other person. And that was too long. If the recurrence had been on a higher frequency or shorter time return period, then we would have possibly seen a better result. But for now, I would say if you have an oscillating fan that takes time, it goes on you for a while, and then it goes away for too long, you're basically losing a lot of its benefit. And that's the conclusion of that. Yeah, that's just shown there. And so my colleague Hui Chang will talk about some of the other studies that we did with the same test setup. Do I have to give you this thing?
Thank you, Ed. So I'm going to present, first I'm going to present 2 lab studies. The goal of these 2 lab studies is to test to what extent how warm the ambient can be that the fan can still provide comfort. So we tested 2 fans. One is the ceiling fan, and another is the desk floor fan. So the test condition, the brown one is the test condition that Ed mentioned at 82.5. And in these 2 tests, we test a matrix of test conditions. We went from 79 to 82.5, and then go all the way to 86 degrees. And then for the humidity, we tested 2 levels from 40% to 60% and 80%. So total, we tested 6 ambient conditions. So the results I'm showing is for the ceiling fan results. The results from the floor fans are very similar. So I'm not presenting the floor fan results. So the vertical axis is the comfort. The comfort, if above 0 means comfortable, positive means comfortable, and then negative means uncomfortable. And here shows the 6 tested conditions that show in the previous slides. And the red line represents without fan, the comfort level without fan. So you can see it went beyond uncomfortable in the warm condition, and it's quite a large difference between the 2. The top lines are all the test result with the fans. So you can see up to 5 conditions, almost up to 68 degrees, and then 60% RH. The comfort level, basically, they're the same. There are not much difference. Just providing by fan, you can cover them from 79 to 86. Except the last one, the comfort was slightly lower, but it's all way above comfort line. The neutral line is still on the comfortable side. And if you look at the perceived quality, again, the vertical, the red line represents the perceived air quality. So how do you perceive the air quality? is the condition when there was no fan. And the vertical represent acceptability level of the perceiver quality. You can see with the fans, those are nothing related with the fresh air. It's just by providing fans, then the perceiver quality always much higher than without fans. And Ed later on will present a little bit more in detail why that could, what was the reason. And this slide shows what are people's preference for their air speed. The left chart is from the ceiling fan, and the right chart is for the floor fan. Floor fan is people chose their own speed level. This is how they located their speed. Left fan is we set up the level and ask them, you want to more or you want to less? And we chose the velocity that people say, this is right, I don't want to less, I don't want to more. We put here. So the two charts represent people's preference for the fan speed. So sometimes I think when we talk with industry designers, they don't know how people prefer fans and think, oh, maybe the 1 meter per second is a pretty terrible speed and we cannot produce. Actually, 1 meter per second, if people chose, they often chose more than that speed. And 1 meter per second, probably if you walk in the speed 1 meter per second, that's how much speed you feel. It's really not like a hurricane or something. So that's the people's preference. And this chart shows the energy. And the two charts shows the two energy fan. One is the ceiling fan, one is the floor fan. And you can see up to the conditions we tested at 82, people's energy is only about 5 watts. So those fans, a fan can be very energy efficient. When we up to 86 degrees, then the fan can go up to 7 watts, or the highest one was 10 watts. So the power use is very effective, very efficient. So after this two tests, which we tested in a warm and kind of humid condition, a little bit higher humidity. And we did another test. This we call the study 4, is to test the fan effect in sport facilities. So in the sport, because people may use the space, may not use the space, it's inefficient if we air condition it all the time. So fan will be a ideal selection to put there. When you use it, turn on them. When you don't use it, you can turn off it. So what we did is, again, the test condition, we tested 4 test conditions. 68 degrees is represent the reference condition. That shows you only use air condition to cool the room, but without using fan. So that one was for the represented by the green dots, was the reference condition. Then we tested with fans at 68, 72, 75, and 78, go all 10 degrees higher. So what was we did the test at 3 different levels of mat level. It's the mat level 2, that's a slow riding of the bike. And mat level 4 is a medium speed of riding. And mat 6 is kind of a high speed of riding. It's more or less like me, probably I couldn't do very long for mat 6 level. And we have 20 subjects participated study. And this shows the results. Each line represents one level, one mat level. So the green one shows if you don't have the fan, that's the comfort level. Vertical, again, is the comfort level. So if you follow one mat level, let's say follow the blue level, blue line, that's a mat level 4, then you can see when the air temperature increased from 68 to 72, 75, all the way 78, just by providing fan, actually the comfort, you can receive the same comfort level as in the 68 without fan. So this is true for both MET level 4 and higher MET level 6. Even at 6, it's right at the border of comfort, but still, in the by using fans, the comfort can be maintained same as the low temperature at 68 without fan. And the green ones was a little bit slightly lower. Part of the reason was the MET level wasn't that high. When we provide some fan, then actually they feel cool. They don't need the fan. That's why the comfort was slightly lowered. So now I'm summarize a couple of related studies that we use air movement to cool people. So this one shows a chair. This chair we cool people basically by 3 fans in the chair. This you can see the fan to cool the back, and then you see another. Actually, we have another fan, 2 fans on the bottom of the seat. So total together was about 3 watts. Each fan costs about 1 watt. And we have this chair tested in our lab. In the lab, the test result you can see. You can see the white box, a box represent the condition with the chair when you have this chair cooling the 3 watts fan running. And then the green box represent without a chair. Then you can see a huge comfort increase. It's a 2 units level increase just by this air motion, small wattage adding to this condition. And then when you see the sensation, that's the right side of the chart. The green, the chair, the fan can bring the condition without the chair was warm back to basically the neutral condition. That was the white box. So this test condition is under 84 degrees and then 50% RH. And then the further, after the lab study, we did another field study. We selected about 24 people in the office, in the campus. We gave them the chair and a little USB fan. In the USB fan cost 1.2 watts. And we gave them and surveyed them before and after having this cooling cooling by the chair, by the fan. And then the results, this is a summer condition. The building was internal load dominated as kind of warm. So you can see when there wasn't any fan, then the acceptability rate, that's in the y-axis. This is the percent of people acceptable. The red box represents the acceptability rate without the fan. Then the average of them maybe cross the temperature from 73 to 80 or 81. Average them probably around 50%. And when we gave them the chair and the little USB fan, then the satisfaction rate is all around 80%, a little bit higher, a little bit lower. 80% is the target for the ASHRAE standard. They target to make 80% people comfortable. So that's the field study, how people, we surveyed them and asked them how do they feel the result by this small fans. So the last 2 slides I'm going to show is we also did a literature study. We gathered in the literature other people, they did the fan study. This including 3 types of fans in this chart. The round dot represent the desk fan, and the cross represent the ceiling fan, and the box rectangular represent the box fan. Sometimes they have a more uniform fan. So these are from other people's studies. You can see from the temperature, you can see from the top was Fahrenheit. In this warm zone, from 79 to 86 or maybe even higher, so 87. People using fans, they can all make them comfortable. I make them green because they all made them comfortable. So green represent comfortable. This paper is just published by Building and Environment. And you see the energy saving chart that Ed showed that we call the COP, the lower COP. That shows the higher if you can expand the ambient condition to let the ambient float, then how much energy you save. Then the top one, this is the COP and the lid. The lid shows how, when you expand the dead band, how comfortable was maintained. Then the lid, the Y shows the it's on the right-hand side. The axis shows occupant satisfaction rate. It's all most of them are above 80%. So the lid is well covered. The cup means you can expand the design set point to make the room float more, but you are able to maintain the comfort by most of them are the fans on the right-hand side to well maintain their comfort. So now I'm switching back to Ed.
Thank you. Okay, well, thank you. We know that CARB is interested in air quality, and so we felt we better talk a little bit about some of the implications of air quality of this type of air motion work that we're doing. Prior to this study, we had done a series of studies, two big studies of air motion on people where we used air coming out of nozzles. You can see in the pictures the nozzles are to the sides of the people. They're two jets. We tested different nozzle sizes. These were the maximum size that we tried. They blow not at the head, but in front of the head so that the two jets collide. And out of the collision is a torus of outflowing air that kind of feels like you've got a breeze in your face, even though there's no source up ahead of you. This was a very nice kind of technique that we found useful for lots of purposes. And there were papers published on this, which I suppose you can find on our eScholarship website. But out of those studies, we came up with this figure, which is, we were asking the same perceived air quality figure that Wei Chang had mentioned. This figure is the same kind of figure that across a wide range of temperatures, the perceived air quality is measured. Now, in the literature, people had published the conclusion or the impression that air motion is a function of temperature. It's a linear temperature. The colder you can make people, the better they'll think the air quality, but when it gets warm, it's really bad. We, first of all, couldn't find any effect on the cold side, that you're getting any better when it's cold. If you look at the blue line on this figure, it kind of goes straight, flat across when you have this TAC means task ambient condition, which is the old name that we use for what are called personal comfort systems, PCS. So that was the first thing we didn't find. The second thing is we did find that it dropped off with temperature above 25 Celsius, which is 77 Fahrenheit, when you had no air motion. However, when you provided air motion out of those nozzles, and that air motion was room air, those nozzles were just blowing air from the same space that the people were in, so it's not fresh air. You got this perceived air quality leveling out. It's a good level. It's 2. It's well above the neutral line, and it's basically the same as it is in the cold situation. We tested 2 types of air motion and so forth, and basically we find this thing again and again. So that suggests that maybe perception of air quality is not just a function of temperature. It's only a function of temperature if you exclude one of the big heat exchange variables that people have that maintains their comfort, which is the air motion. So if you plot instead the perceived air quality, which is the vertical axis here, with the thermal comfort, which on the x-axis, here we see a nice linear fit that shows that the more uncomfortable people are, the worse, the less acceptable the air quality will be. But if they're feeling comfortable, even if it's a cold temperature and they're getting their feet warmed by our personal comfort systems, or if it's a very high temperature and we're blowing air on them, they're comfortable. And this, I think, is a fundamental change in what the published results were prior to the study. So then we got to thinking, well, okay, what's the cause of this improved air perception? You know, the temperature is higher, is much higher. It's not a temperature effect. What is causing it? And is it, in fact, just a perception of air motion that you might somehow mentally associate with being outdoors because there's a breeze in your face, so you think you're outdoors and therefore the air quality is supposed to be good? Or is it something else? Is it more fundamental? So we got to thinking about the body's plume. The body has a plume of heated air that rises off the body, and it also comes up from the floor. It pulls up whatever's on the floor, and it also adds your bioeffluents to the plume, and all of it passes up, goes by your nose. And so we thought we'd take a look at that. So we got this is our electrical thermal mannequin named Monica that is used for a lot of our tests. And she's heated the way they got the same skin temperature as a real person. You can see the plume rising up past her nose on the left. But then we added a collar to deflect that plume. And it's kind of the way the Dutch had collars. One wonders why the Dutch used those collars. It deflected most of whatever was coming up from their bodies. And we did a human subject test of this. We couldn't standardize the odor from perspiration. We tried, but we couldn't do that. But we found a very powerful source of odor that was persistent over time and also perceived by the person over time. It's a mix of three, camphor, menthol, and eucalyptus. And you put it on your body, and it's supposed to clear your sinuses. You know, so it works for several hours. And so anyway, we put it inside their clothes here, and we gave them the collar, and we took the collar away, and we gave them the air motion through those nozzles, as shown before. And here are the results. The scent intensity without the collar is the highest. The collar did a good job of deflecting a fair bit of it. It's kind of down here in the middle of this axis. And adding, or actually taking the collar off but blowing the air motion laterally in the vicinity of the nose had the biggest effect. So what we've got here is a disruption of the plume by what might be called invasive air motion or ambient air motion, which would come from a fan of various sorts. And so there's a physical thing going on here too. They perceive it, but it's also, you're actually improving the air quality of these people, because to the extent that air quality is something that your bioeffluents are involved, or something that you may have pulled up from the carpet that's passing through your nose, the room air itself from up here is probably cleaner than either of those, and so you've actually improved them. So we take a little look at this. I'm borrowing slides here from a colleague who's visiting with us at this point, who did these. So some of these are Schlieren pictures that show the plume. It shows that there's a lot of motion around the head, around the breathing zone. But that image in the middle shows that it comes up from the floor. And for seated people, the plume is very thick in front of their face. Standing people, it's narrower. The air temperature in the plume is a degree or two higher than the ambient. And so there's been CFD studies of this done. This is a picture that I won't go into huge detail, but there's the pure convective boundary layer on the upper left, and then there's opposing flows of 0.3 meters a second and 0.4 meters a second. Opposing means if the plume is going upward, the ceiling fan will give you a downward flow that opposes the plume. And what is the effect of that? Then a transverse means that you've got the flow coming from the front, lateral, horizontally coming at the face. Velocities here, 0.3 meters a second. In feet per minute, that's, you multiply by 200. So that would be 60 feet per minute. And so it turns out that the flow in the plume is about 0.3 meters a second. And so if you have an opposing flow, you end up with 0 kind of in that middle upper picture. If you get the speed up to 0.4 meters a second, some of you may want to think of it in terms of miles per hour, for example. That's 1 mile an hour. That's not very much. It's enough to blow the plume off. You can see the red vectors are all in the downward direction there. And the traversely also, you're able to blow the plume apart once you go above 0.3. So, and then there's a great big matrix of results, which I won't going to go into. This has to do with how much maybe a cough that somebody emits 3 meters away from you. What's the effect of the plume in terms of carrying the cough through your plume and so forth. There's a relationship to indoor air quality, but it's complicated. It depends if you're thinking of the invading air being, including pollutants or not. All right, so that's one piece of the puzzle that people talk about and that we felt we had to address, and so we did something on that. Another thing is that in California especially, but really anywhere in the world, it turns out that cooling buildings with radiant systems, basically cooling by circulating water through panels or parts of the building structure to cool the structure itself, is much more efficient than air cooling. And this is largely because water has so much more heat capacity than air. You can move a lot less of it around, a lot more quietly and everything, and you can cool that way. So radiant cooling of the floor or the ceiling especially are the main opportunities. They promise great savings potential in California, and we are pursuing the study of these things intensely because of that reason. But they have a problem because you have to be in view of these radiant surfaces, say overhead or down below, for you to exchange energy with them. And so a radiant ceiling made of concrete, it tends to have to be a conductive surface, which means it tends to have to be hard and reflective, causes bad acoustical environments. So again and again, you get these buildings with nicely sculpted concrete ceilings or things like that that have acoustical difficulties. It's hard to put enough acoustical treatment into the walls or in panels or in the furniture to make up for that panel. So people like to have acoustic treatment in the ceilings, like here, by panels that usually hang below the actual structural slab that's being cooled. Part of it vanished, but it shows that the heat transfer is being blocked, the radiant heat transfer is being blocked by the radiation, by the acoustical panel, which is an absorptive, insulating material by nature, interfering with your view to the surroundings. Normally, you would want to have 60% radiant heat exchange when you have a cooled surface, and about 40 takes place by cold air dropping off the cold surface. This is when you have a so-called TABS system, a thermally activated building system, where you're running cooled water pipes in the concrete structure overhead. So you have this problem. Your thermal efficiency is dropping off when you apply acoustical. So we wanted to study that, and it did the work with a CFD experiment, where we had a radiant ceiling, and then we had these various sources down in the space, inlets and outlets all kind of modeled as well. And then looking at it in plan view, the configuration tested, there was a bunch of panels, some of which we would open, different percentages of it would open, and we had an opening in there where we're going to put a fan, because our hypothesis was that sure, you may block the radiant exchange with the environment overhead, but perhaps if you had a fan, which could be low wattage, could be a very low power thing, it could force the convection to increase, which would take care, maybe offset the loss of radiant exchange. And so there was a kind of a complex matrix of tests done, and we blew the fan up and down, both directions. I should point out that this kind of a treatment of the ceiling with acoustical panels that are not going ceiling wall-to-wall like in this room, it's called a cloud when you let the edges be exposed and you have some paths for things for air and also for sound waves to go up around the cloud. They are actually not less efficient than this kind of total ceiling, because when you have these edges exposed, the sound is absorbed top and bottom on the panel, which is not in this kind of wall-to-wall treatment. So you actually get better treatment if you can start opening up the acoustical ceilings, and that's what we would have to have for the test that we did here. And so this is just a quick synopsis of complicated results, but we have an upward flowing fan on the lower image and a downward flowing fan on the upper image. Right? Yeah. And and basically different panel openings, different speeds of the fan, stuff like that. No fan, and so forth. And sure, if you have no fan built into your cloud, your efficiency of your heat transfer with a radiantly cooled ceiling drops off. It's expected. It dropped off, and it actually isn't as much as I might have expected, but individual occupants would be maybe blocked more than this analysis predicts, because some people will be really blocked by the radiant exchange, might be blocked by the panels being overhead. But when you increase the convection portion of this, the efficiency of the system is actually higher than it is if you have absolutely no acoustic treatment whatsoever. And it remains high. It's true at the low speeds, but also it remains high where the coverage is high, sorry. So that is promising. We're presenting these things, and each one of them, if they were showstoppers for air motion, we would emphasize that. But basically, what we're saying is these are promising developments, each of them. And so I want to talk a little more about some of these. There are quite a few issues, but at this stage, things look promising enough that I think we should somehow be focusing on how to get the industry to adopt ambient air motion globally. So I'll just show a few things here. One of them is that, as I mentioned before, there's very little design guidance on how to design for air motion around a human being in an office environment with sources like ceiling fans or wall fans even. And then there'd also need to be better standards for categorizing how efficient fans are. It's kind of like evaluation standards. And so at this point, ASHRAE has a new standards committee for evaluating fan performance efficiency. It's called Standard 216, and we're serving on that one. And it'll be something to do with the amount of comfort that you can provide per watt that's used by the fan motor. And so that. Here's a test of fans and their efficiency. They're normally always evaluated in a no furniture situation, but most people work with furniture, and there's at least a desk in there. And when the fan airspeed comes down, you can imagine when you have no desk, it comes to the floor and then it blows laterally across and it cools your ankles. But if you have a desk, it hits the desk and comes laterally across at your mid-body height, which is actually what you want. And partitions may or may not play with that lateral flow that's taking place at mid-body level in various ways. And so you kind of have a complicated thing there that probably requires a model to predict so that you can position furniture and fans or determine how you should play with these different elements. This is an image that, we didn't place that one, did we? it basically shows that there are different profiles of airspeed under fans with different distances of the center of the fan over the desk. Which leads me to the thought that maybe we could focus the airspeed on the occupant without maybe blanketly providing it through big fans. Man, okay, and so I'm going to talk a little bit about small fans. Wei mentioned the USB fans, which are a new development, which we believe has been encouraged by the Japanese earthquake that caused them to have to mandate shutting down of HVAC systems in the afternoon in the hot humid summers in Tokyo. And so people have been buying these USB fans that plug into your computer, which run off of that 3-volt signal or source. They only use 1 watt, or 0.8 watts, and they provide 2 meters a second of airspeed, which pretty much covers your facial region. It's not as effective as a ceiling fan, but it's more than half as effective. And for 1 or 2 watts, you could have 2 of them. And so they could be positioned, on your desk, or they could be built into your furniture, or they could be hung over from overhead. Here, this is a conceptual thing, but we have played with this type of thing in our lab, and it's promising. The little fan that we show there is one that we used with our combined comfort system, foot warmer and fan, which is a nozzle fan, and it it does the same thing for about 1 watt. It blows 2 meters a second for 2 meters, about 6 feet. And you see the little white thing in the middle of the hub of the fan, that's an occupancy sensor. So if you're not in front of this fan, you're not in the view of the nozzle, the thing turns off. So it's kind of a built-in thing that gives you breeze. You have knobs to control it. So that's something in the heading that the future. It's a promising opportunity. I should say these USB fans cost anywhere between $6 and $20. They're almost free, and they're dead silent. And if you put your fingers in them, it doesn't hurt. And they run on magnetically levitated bearings. They're very simple, and quiet. So it's a wonderful thing that these new things are now available. I should say, I'll show in the next slide, the appearance of fans has become acceptable. We aren't totally linked to barroom, saloon kind of fans with less light fixtures hanging off the bottom of them. We actually have things available that architects can accept and are beginning to, and powerful advertising going on by some industries to penetrate this high-end market. And I should say intelligent controls. I mean, the other big thing going on in the building industry, that's just getting started, is the Internet of Things is affecting thermostats. We're getting past the kind of balkanized control systems that control buildings. We can get the signals out of the different actuators and sensors in buildings, put them into something that processes the results in a way that you can control the building in a more distributed and intelligent way. And these fans have been linked that way too. Some of these fans now have temperature control. They have ways of linking perhaps to occupant monitoring things like these Aristify bands or things like that. You can tell if you're there, what your activity level is, whether you're really sleeping well or not, and it can adjust the fan speed for all these things. So there's going to be a lot of potential to sculpt or modify air motion in many ways as we get more intelligence, or wireless intelligence basically, in buildings. Okay, so we believe the momentum is underway for air motion. There's lots of promise for manufacturers and stuff. There's virtually nothing you can buy. Well, I shouldn't say that. That's kind of, basically there's a lot that's coming on the market soon. The other point is elevated air motion should be the base condition before the compressor turns on. This is not something for naturally ventilated buildings only, or buildings that have no control otherwise beyond fans. We can have air conditioners. It's just that the compressor shouldn't come on till the fan is past its useful speed, and then the fan should remain on. Whenever the air conditioner is running, the fan should be at its maximum speed, because that means that the air conditioner will be at its minimum load. You know, and so if you operated a building that way, you'd have to resize virtually major buildings. You'd have to have a way of reducing the capacity of the chilling that's in these buildings, but you're going to save large amounts of energy, and that's what we want to do. This is just to show that fans are becoming sexy. These are being published in fine home building and architectural journals. There's aggressive pushes to have beautiful objects to somehow stir up the air. I think this is our chamber with the same couple of guys who worked on various our projects.
Let me first ask anyone here if you have questions. I'm sure Professor Ahrens and Dr. Chang will be happy to answer them. And why don't you go? Yeah, why don't you handle it?
My question is, first, no fan curve results show the neutral comfort up to 85 degrees. How can this be? So I'm going to show the slides. I think that came from this is the one. I think if you look at the no fan follows the red dots. No fan follows the red dots up to 82 degree and then 80 RH. That's if you come down to look at the bottom, that's about 85 effective temperature. So the comfort was still above the neutral comfort zone. So this is the question, how it seems to be very warm. People are still in our lab testing is still comfortable. So this is truly, we saw this when we thought about ourselves, but it's actually repeatedly show different conditions, not only one time to show that. See this a different test. If you remember, this test condition is 82.5 and no fan, the first box, the comfort was also in the comfortable side. The bar was above 0. So why? There are two reasons. One reason is in our test, people are seated. During the test, they answer the survey questions or they are allowed to do the internet browse. But after all, they are different from the real office. You stand up, you talk with people. The activity level is lower. So slightly lower. In our test, although we try to periodically during the test, after each session, we let them to stand up and step up and down, trying to boost up their metabolic level. But I believe it's still lower than the real office people's MET level. And 0.1 MET level is quietly sitting is one. If you're periodically walking, it's corresponding to maybe 1.2 MET. And 0.1 MET increase corresponding to about 1.4 degree difference in temperature reduction. So basically, as your MET goes to higher and higher, then your comfort temperature goes to lower and lower. That's the part of the reason. So that should be shifted. If you're in the real office, you have more talking communication, then shifted down maybe 1 or 2 degrees. This is one reason. And you see our mat study in the gym there, the common temperature was 68 because the metabolic is high. And there is another reason. There is another reason we believe in our test when we observe, survey people, we see this, people do adapt. This adapt means I shouldn't use adapt. Comfort is a zone. Comfort is a range. It's not the one set of temperature. I can be comfortable at normal people think, oh, the comfort should, we design temperature around the 74, 75. But actually, I have a zone. I can be perfectly fine at 68. I think even especially women. So actually, comfort never been one single point. It's a zone. We maybe look at the closer to the upper zone of our comfort that range. So that's another reason I can be comfortable in lower or higher range. So that's another explanation. This question is, yeah.
Okay, so I have a few questions here. One of them is, how do you control condensation in a radiant cooling system? This is actually pretty simple. You keep the water temperature in the inlet manifold, whatever you supply to your system, 4 degrees Fahrenheit or so higher than the dew point temperature. So somewhere in your system, you measure dew point, and then you just don't supply air or water that's colder than that to the system, and you'll have no trouble anywhere else because the system will be absorbing heat. If you go to the REHAU website, REHAU, there's a lively discussion about that topic. There's a video about that, but basically the point of the video is what I just said. You just keep, it's not hard to control for condensation in radiant cooling. Obviously, the capacity is not infinite. You can't run down as cold as in a coil, and you may have to do your dehumidification elsewhere in the radiant system. When dealing with the incoming air, the latent loads need to be taken out by some other kind of coil. Okay, the other question is, it says on slide 34, the chair fan and slides 35 and 6 from the literature review suggest that there's an upper limit to the effectiveness of fans in cooling the body. Do you have plans to test subjects above the low 80s? Well, we've actually tested up to 86 and found people comfortable at 60% RH. It's at 80% RH that they tip over the border. We found that the line that's in that that's on the ASHRAE comfort zone is almost right on in terms of predicting this going from 80%, dropping below 80% acceptability under those conditions. That's what the comfort zone boundary is. So we believe that we have a pretty good feeling from our studies and a number of studies that have been done recently in Asia, especially, even in Europe, the bastion of still air and cold conditioning, cold and dry, they're finding the same results. You're up in the mid 80s, you can be comfortable with air motion. The other question is, for temperatures above 90 Fahrenheit, when the humidity is high, a fan can overwhelm the body's ability to stay cool. Such conditions can occur for prolonged periods in homes during heat waves. Public health agencies in Canada and England have advised against using fans under such conditions. This is true. I mean, at a certain point, the air temperature will be higher than your skin temperature, and it's at that point, increasing the heat transfer coefficient is not going to do you good. However, the evaporative portion of your heat loss, depending on the humidity, will allow the air temperature to go above your skin temperature because your skin temperature is going to cool by evaporation. It's only at 100% RH that you can use air temperature as your only metric of whether heat is going into your body or not. In other words, you can be comfortable at something well above your skin temperature. You can be comfortable at 100 degrees if you have sufficient evaporation going on and air motion. But we would say in most buildings, if you had an air conditioner, you don't want to let the temperature go to 100 degrees inside. You would try to hold it at 86 degrees inside and use a tiny fraction of what you normally use when you run your air conditioner, and make sure that you've got air motion going at that time. Right?
Had an additional question on the chairs. Did you use a market available type of system, or is that kind of a customized ventilated chair that you created for this study?
Designed that chair and built them. We built 80 of them. Fortunately, someone else has now licensed this thing and are building them. And so they are coming out, I think, in a week or less from some startup called Personal Comfort Systems, Oakland. But there are lots of opportunities, I would say, to make chairs like that. What we were focusing on was to make it as absolutely as efficient as I believe we're close. You can't do much better than, if you can cool people down that far for 3 watts, you're doing pretty well, and it works very nicely for heating people too. And I think it's, the pieces that are involved are not inherently that expensive either. So I think this is a very, very promising technology. But as you saw, or as the person mentioned who sent in this comments about the upper limits, the chair doesn't do it all by itself. And part of it is because of this plume situation. You really want to get some cooling in the head, and the chair doesn't cool your head. So that little USB fan actually helps make the chair thing work higher into the hot side.
That was what I was about to say. It also has a small USB fan and the chair alone. But in general, just the air movement you apply to head, that's the most sensitive for cooling. You do want to apply some air motion to cool the head. And then for the any body part, it's just a small wattage. This can be very effective. This is we saw from all the different body parts. Actually, in our lab testing, we use those cooling to cool every body part. So we tested the leg, arm, and then to see where is the most effective body parts. We should add this cooling to which body part, or where to add them to the heating. So that's actually, and I do want to add another comments for the previous question, said in the heat wave, so the fan can help the environment maintain people comfortable in a high temperature. And I would like to add one more thing. Note is that those fans we are using nowadays, the energy efficient fans, they're all the DC motor. They are not the AC motor. Otherwise, they cannot be that efficient. So their DC motor, they are only about you see in the test up to 83 degrees C, or they only degrees Fahrenheit. They only use about 4 or 5 watts, so very low. And then the advantage is that they can be battery driven. Actually, so that's one thing you can use in a heat wave, or maybe demand respond. So you just charge them in the evening, because they're all the DC motor. You can just turn on when it's needed, or when the blackout, then what the power outage, then you can turn on those fans. So that's another advantage.
Oh, great. Yeah, here's a question. Did you look at potential peak load reductions associated with expansion of the envelope of comfort? Since half of California's peak electrical loads on hot summer days, and it's due to air conditioning use, this seems like an important potential benefit to explore. So that's part of it. This is a demand response. These devices, all the fans, the chair, are seen also as demand response enabling devices, because their wattage is so low that you can turn off the central air, and you can coast fairly high temperatures before you're going to complain. And as we mentioned, the chair, for example, runs on a battery, and it runs for a whole week in cooling mode between charges. Heating mode's a little more difficult because it's 14 watts for heating, but so that takes 2 days. But this means you can be untethered, you can and and response events, you're totally invisible. Oh, another one. Not too late. I'm one of those people who is adversely impacted by light flicker. You experience our ceiling fan installers aware of the flickering light phenomenon that results when fans are installed below lights. Yeah, we would not recommend installing. However, you can position fans. You can raise their position in some cases. You can hang lights down. In general, lighting is a thing about which we're very optimistic and happy because the sources are becoming smaller and smaller, and using less and less energy, and you can pretty much hang them anywhere. And so to drop light, the LED sources down to the level of the fan blades so that there'll be no flickering is becoming easier and easier to do, even in very conventional kind of office.
Are there any other questions? If they're not, let's please thank Professor Ahrens and Dr.